兴啊，大家来参加这个 seminar。我们办公室的同仁啊，接到这个安排这个演讲的时候，他们就安排了一个教室。我就说，你们太小看了韩教授的吸引力，应该弄个大一点的，至少要有3位数，就找了一个100多个人的纪念馆的演讲厅。结果我还是 underestimate 韩教授的这个魅力啊，所以我们又换了这一个更大了250个位置的啊，不过还是不够，外面还有人 stand line， 因为没有报名。不过没办法了，因为清华就最大演讲厅就大概在这里。那今天很高兴呢，跟各位介绍韩松教授其实你们应该都知道了，不然的话不会这么多人要来听演讲，对不对？不过我讲一点，就是说，有一本书呢，叫做《Outlier》，不晓得各位有没有看过？的 Malcolm Gladwell 写的。那他来观察一些历史上一些重要的成功人士他有一些观察，比如说 Steve Jobs 跟这个 Bill Gates 呢，都是1955年出生的。还有那个好几个Bill Joy Bill Joy， 还有这个Eric Schmidt 这些。那为什么1955年的出生就很厉害呢？那他就发现呢，在往前往后呢，其实也都有同样的现象。这1955年出生的人呢，在 PC 刚出来的时候呢 ，microprocessor PC 出来的时候呢，他们大概都20岁左右。那往前呢，你可以看钢铁大王卡耐基呢，这产业刚开始的时候呢，20出头岁的人，最后就很成功。那再往后看呢 ，Internet 时代你看 Google 的 founder、Facebook 的 founder 都是一样20出头。那我们现在在这个 Deep Learning 时代呢，也就有一批这个20出头的人，就是这个样子。那韩教授是其中一位。所以这是很难得的机会。那韩教授是北京清华大学毕业，他非常年轻现在还不到30岁。那他毕业以后到 Stanford 大学念博士学位。那念书的时候呢，他有很重要的 contribution 在这个 deep learning 的技术，等一下他会讲。那不止 academic 发表 paper 引起全世界的回响，那 citation 的数以千计within a couple of years。更难得的呢，他跟这个北京清华的老师还有学弟同时就把他的技术放的一个公司叫深建科技 DeepFi。那 CEO 呢是23岁的姚宋，2年前也来过我们这里。他的老师呢也是30出头岁的，叫汪玉，也来这边演讲过2次。那这公司呢，不久以前被这个 Xilinx 以很高的价钱收购进去了所以不止 academic， 还有产业的impact。那当然呢，这么好的人最好的学校就 recruit 去当教授，所以他从去年开始就在 MIT 担任 assistant professor 来主持这个 lab。所以今天呢，我们很高兴大家鼓掌欢迎韩教授演讲。
谢谢林老师的介绍，我一次来到台湾非常 exciting。今天特别感谢林老师，作为北京清华校友，这次也是第一次来到台湾清华。然后第二个 purpose 就是特别感谢之前在做深建科技的时候，林老师给我们的很大帮助，包括在 GOC 做流片的时候，最后流出的效果不但meet 了 design spec， 也超出了 design spec， 所以这次特别感谢。第三个 purpose 就是现在在 MIT 做 professor， 然后也希望创造更多的交流和分享的机会，促进两边的交流。OK， 所以今天我带来的 presentation 是Hardware Centric AutoML 第 design automation for efficient deep learning computing. Deep learning computing 现在无论在端上还是云上都有很大的 demand， 有很多新的 application。那我们做 algorithm hardware co-design 增加它的 design 效率。但是这是一个非常大的 design space， 我们有算法，我们有硬件放在一起，我们既需要有algorithm engineer， 又需要有 hardware engineer。那我们能不能做 design automation， 用 AI 去设计这样的整个design flow， 就在做一些工作。在进入正题之前呢，先介绍一下 MIT 最近在AI 上面的一些big initiative。For example, recently we have launched this MIT Quest for Intelligence, which is a pretty big initiative for core AI and also the bridge for AI. So for the core for AI, we focus on both vision, NLP, speech, and other machine learning algorithms. And also for the bridge for AI, we focus on the tools, accelerators, hardware, infrastructures for AI. And also, I think we have recently launched the new College of Computing, which is a very big initiative on computer science and artificial intelligence. So as a recap of the background, the virtuous cycle for deep learning computing. So hardware played a major role in the recent development of artificial intelligence. For example, more users will generate more data, which require more powerful hardware to process those data. For example, those high-performance GPUs and TPUs allow us to train larger models, which will have a higher accuracy when we are doing prediction. Given those more efficient inference hardware, for example, mobile SoCs and also our data centers, we are able to provide better user experience in running those algorithms, which will attract more users and generate more data. So this is a virtuous cycle. However, Moore's law is slowing down. The demand for data is increasing, but also Moore's law is slowing down. So how do we deal with the clash between the supply and demand for computation? So our mission is to make AI more efficient. So we are having an AI algorithm. We want to land to a real application scenario. From the hardware perspective, we want to have the AI algorithm run faster with less dollars, taking less memory, less computation, less networking, less energy. And from software perspective, we want to have less supervision, higher accuracy, less vulnerable to attacks, and make everything automated. So to try to solve bigger AI problems. In order to achieve this goal, my research lab focus on those three areas. One is my last name, but also it stands for hardware, AI, and neural nets. So for hardware, we want to have high performance, high energy efficient hardware. A stands for AutoML to make design automated architectures and accelerators for AI. So for architectures, we focus both on the neural network architecture and also on the computer architecture to build specialized accelerators for artificial intelligence. Finally, we also design efficient algorithms for neural nets. And we target small models for inference, which make it fast and small. And also scalable systems for large-scale distributed training and also specialized silicon for all these applications with specialized various silicon. So introduction of an overview of the research lab, we focus on three different layers. On the application layer, we focus on those computation-intensive AI algorithms, like video understanding, which is takes more computation than just images, but have more usage in recent years. And also 3D recognition, which is what they use. For example, point cloud is what they use as autonomous driving. And also the tools, like architecture search, how to automatically search an efficient neural network architecture given the hardware and your target task. And also my previous work on deep compression, how to aggressively compress a neural net so it takes smaller memory, less computation, doesn't sacrifice accuracy. On the hardware side, we build specialized architectures given the new demand from the applications. For example, sparsity. After compressing the model, a dense neural net becomes sparse. And also multi-precision support. Different layers have different demand for accuracy. So how do we have the same piece of silicon to support different precisions? And finally, other specialized primitives such as intersection and union, which we recently find quite useful in efficient deep learning computing. So here is a quick overview of my PhD thesis. For work, first to work on algorithm perspective, how to compress neural nets by pruning like twin quantization to reduce the amount of parameters and also to reduce the bit width per parameter. Next, we designed the EIE accelerator, which stands for efficient inference engine that works directly on the sparse and compressed model. And we later designed the efficient speech recognition engine, which is the LSTM accelerator, prototyped in IPG, and now is also available on AWS Marketplace. So to understand the later presentations, I will spend a couple of minutes to introduce the background of model compression. Work back in 2015, which is the foundation of DeFi Tech, which is a startup we later founded 3 years ago. So pruning, the target is to remove the amount of parameters and connections to save computation and save memory. So we prune both the synapses and also the neurons. And later we can also do block sparsity to prune a chunk of connections so that the dense neural network will become sparse or have less number of computation memory requirement. So actually, human brain has this process as form of pruning. According to this study from Nature, a newborn child has about 15 trillion synapses in the brain. When it grows to 1 year old, this number surges to 1,000 trillion. But as it gets to adolescent, this number didn't continue to increase, but begins to decrease. No question?
Excuse me, Professor Heck, can you speak more loudly?
All right, I'll speak more loudly. All right. So this number didn't keep increasing, but begins to decrease. Okay. So the pruning process happens. When you learn, interact with the world, not necessarily more parameters means better performance, but human brain has this natural process of pruning. And failing to prune can cause diseases. For example, according to another study from Nature, failing to prune, this is a normal synapses that gets pruned. This is another synapses that fail to prune. Failing to prune will cause a disease called schizophrenia, which is a mental disorder that's called faulty perception. So pruning happens in human brain. How about for deep neural nets? So 4 years ago, I experimented with AlexNet. For different layers, those green parts of the synapses you can safely prune away, and those blue parts are actually the useful parameters. So for conv layer, we can remove about compress the model by about 3 times. For FC layer, about 10 times. So if we naively prune the parameters, you see 80% sparsity, we will have about 4% accuracy degradation. But for 80%, if we can retrain those remaining parameters, we can safely recover the accuracy, no loss of accuracy compared with the dense model. And if we iteratively do the pruning and retraining, we can fully recover the accuracy until we prune away 90% of the parameters, which is pretty impressive. We can save lots of computation and an order of magnitude memory saving. So for CNNs, it works pretty well. How about for RNNs and LSTMs? Does the same pruning works over there? RNNs and LSTMs are widely used in speech and natural language. So given this example, when we are doing image caption, this is neural talk. We can also safely prune away 90% of the parameters without hurting the accuracy. So here are some visualizations. For example, given the first image where a man is playing basketball, the original image caption system says a basketball player in one uniform is playing with a ball. And if you prune away 90%, it says a basketball player in one uniform is playing with a basketball. It's pretty much the same. Maybe basketball is even more accurate than ball, since there's less overfitting. Given the second image, the original neural net says a brown dog is running through a grassy field, versus prune away 90%, it says a brown dog is running through a grassy area. It's pretty much the same, but to save 10 times the computation. The third one, a man is riding a surfboard on a wave versus a man in white street riding a wave on the beach. But if you prune too aggressively, say the last one, you prune away 95%. It says a man in a red shirt, black and white shirt is running through the field. It's getting drunk, so there is a red threshold you need to pay attention to. All right, so pruning saved the amount of computation, amount of synapses and parameters. We can further use twin quantization, which was published in SRC 16, to reduce the bit width bit width per parameter. So rather than using full precision 32-bit, can we use a fewer number of bits to have approximated weights? For example, I colored similar weights but the same color. For example, the blue color, we have 2.09, 2.12, 1.92. And I clustered everything to the same centroid, which is 2. So we need only 2 bits to index into this codebook with 4 entries. And during back propagation, we can collect, do the group by operation to collect similar weights together, reduce them, multiply by the learning rate, subtracted from the initial centroid, which concludes a loop of stochastic gradient descent. And in this way, we can safely quantize the neural nets to about 4 bits without losing any accuracy from less than 50 on the image net. Well, compared with Google TensorFlow, with 4 bits, there are about more than 1% loss of accuracy. So by combining pruning and quantization, we can aggressively compress a wide range of neural nets. For example, AlexNet VGG reception in less than 50, the compression ratio ranges from 17 times to 49 times. And you see from 100 megabytes to only about 6 megabytes, which is roughly the size of SRAM. You can easily host them on SRAM. Well, the accuracy didn't decrease, but slightly increased due to less overfitting. So this is a demo when I was doing internship at Facebook. I helped them build the first mobile model running on the mobile phone and compressed the model by 8 times. Mark Zuckerberg presented the same demo during the Facebook Developer Conference. The demo is showing object detection on a phone, and running the phone to detect, okay, this is a coffee cup. And then we can apply those AR effects according to what it is and where it is. So the most computation-intensive part running on the phone is to detect, do object detection. Being able to aggressively compress the model can make it more faster. For example, apply some AR effects according to the object. And you can even apply rose and flowers. All right, so far we talked about algorithm hardware. But what we want to do is algorithm hardware co-design. Rather than seeing the benchmark and running on CPU and GPUs, we want to say, what is the most efficient algorithm and how to design domain-specific hardware to support those prune, quantized, aggressively compressed, those efficient algorithms. So we want to open up the box to design the silicon according to the best algorithm. We want to design across the full stack. So later I designed a hardware accelerator called EAE, Efficient Inference Engine, for those compressed sparse neural nets. So the key point of EAE is it works directly on the sparse compressed model. We don't save those we only save those non-zero elements. So for every 0 multiplied by 0 is 0. So we save the cycle, not computing them, and we save the memory. No need to store those weights. We store the weights in the relative index with the sparse format. And remember, we encode every weight into 4 bits rather than 32-bit, which saves 8 times the memory. So we store the encoded weight followed by a lookup table to decode the weight. And we did a layout, do the pre-silicon simulation for the whole chip, which led to the later RPG prototype. So the silicon 45 nanometer is about 2 orders of magnitude faster than the CPU baseline, mostly because we are compressing the weight by about 30 times. And also the activation has about 70% zero elements to make a skip. And also we have about 8 times saving from 32-bit to only 4-bit. And also it achieved pretty good energy efficiency. And this is the energy efficiency compared of EIE with different technology node compared with other work. Another saving is coming from we can buffer all the weights in on-chip SRAM rather than having to go to off-chip. Since after compression, the weights is only about a few megabytes, less than 10 megabytes, which fit in the on-chip SRAM. So later, we commercialized the deep compression in my startup, DeFi Tech. which stands for discover the, DeFi stands for discover the philosophy behind the deep learning computing, Honeyford's philosophy. So we developed this deep neural network development kit that includes the model compression, compilation, and also the hardware acceleration. And recently, we frequently update this development kit. It's accessible from this website. So DNTK provided the turnkey solution where we analyze the model, prune it in the scissors to cut those random weights, and also transform it to the format that our FPGA can take advantage of. So this is both image classification and object detection some baselines where we can actually improve the accuracy a little bit on detection task while aggressively compress the model to about 63%, 16%, 40%, etc. This is for a particular surveillance customer where we aggressively decreased the computation from 120 gigaops to only 12 gigaops, while the accuracy maintains pretty much the same across different scenarios. And by cutting the computation from 120 gigaops to only 12 gigaops, we can have a speed up of roughly 5.6 times. Beyond pruning, we also have a quantization tool at DeFi where we can quantize the model, test it. If it meets the requirement accuracy, we can directly deploy it. Otherwise, we will fine-tune the model. So on this different benchmarks, exception resonance, BGG exception resonance, we have very little loss of accuracy, 0.3 to 0.4% loss of accuracy. And later we provided this whole tool chain for model compression. It followed my deep compression paper with pruning, quantization, and Huffman coding. Since Huffman coding gave very marginal improvement, so in the actual product, we took the first two stages as our compression tool that includes the pruning tool and also the quantization tool. And now this whole flow has pretty much become the industry standard to deploy deep neural nets. And also the hardware architecture we prototyped later on FPGA is now available at AWS Marketplace. So if you want to try it, you can come to there. So we provide the whole solution from model compression, from pruning to quantization, to compiling to the hardware architecture where previously we have to store all these weights if we were to use uncompressed dense format. Now we need to save only those non-zero entries, which is a huge saving. We are constantly optimizing the pruning technology. For example, we can do load balance aware pruning to achieve better speed up. Previously, about 5.5x speed up. With load balance aware pruning, 6.2x speed up. So it's really a hardware and algorithm co-design, giving the need from hardware to do load balance. We smartly prune those neural nets. So here are some demo. Here's a demo for before compression. Previously, it runs at 30 frames per second. Now, everything runs at 32 frames per second. And this is an object detection task, where before compression, it runs 16 frames per second and 4 video streams. So only 4 streams, 4 frames per second. You see, object detection run and get stuck a lot. And later, we can run at about 30 frames per second. Doing object detection for the cars, pedestrians, and also bicycles. So given the success and the big performance improvement, Xilinx recently acquired us, and hopefully we can do a better job to make a bigger impact in the state of the world. But the story didn't end. I later joined MIT as a faculty member, but we meet more customers who want to take advantage of such technology. For example, previously when we have only 3 people work this technology, we can assign 3 engineers, right, to do them. later more people want to access this tool. Right? But can we have so many engineers? It's actually very difficult to find. And in my lab, we have only about less than 10 students, right? So therefore, we want to have an automated tool chain to do model compression. Use AI to do model compression, rather than rely on human experience and human efforts to do model compression. So the big picture, the goal is to efficiently design neural nets and hardware accelerators. Previously, we relied on machine learning expert and also hardware expert. Machine learning expert and hardware expert is difficult to find where you can master both techniques. But our goal is to have non-expert, but using our hardware-centric AutoML, then you can click the button, and then it will automatically search the best neural nets and also the efficient AI engine. So this is our initial trial to implement this goal. The first work is called AMC, Automatic Model Compression and Acceleration for Mobile Devices, working with my students. So the idea here is to, rather than using a human engineer to do model compression, and we have developed an AI agent to do model compression. Okay? So we model the problem as a game. Just like AlphaGo can learn to play Go, we want to have this reinforcement learning agent to be able to learn this task of doing model compression. For example, we have 3 layers, and we model the game with 3 stages. Right? And each stage in action is the pruning policy. How much parameters do we want to prune away? And finally, after we complete pruning for the other layers, we give a reward, which tells you whether you win the game or lose the game. So the signal consists of 2 parts. The first one is the error rate. We want to have low error rate. The second part is the flops. We want to have less computation. So you can have both low error rate and also low flops, then you have a pretty good reward. So this is the mechanism. We do model compression in an automatic way. And here we use deterministic policy gradient to give continuous control for the sparsity. All right. So just now we talked about how to model the model compression problem as a game, right? How to design using deterministic policy gradient to give continuous control to automatically figure out how much parameters can you save for each layer. Let's see the result. So this is the result on less than 50 for different layers. The free part is in my PhD thesis, human approved model, where we can reduce less than 50 to 29% of its original model size. But my students developed a much better way to compress the model to only 20%. It's not only much better, but also I used about a week to figure out the best pruning policy. Right? And my students used only about 4 hours to figure out this model, the best policy in an automatic way. And not only can it do better, but also the agent can learn something. This is the sparsity for different layer of less than 50. So it automatically learns the 3x3 convolution and will have more redundancy. Therefore, we can aggressively compress these layers. Well, for those 1x1 convolutions, the IL agent automatically learned it has less redundancy and can improve less. No one has taught it before, but it figured out that this is that as well. And compared with the human design model, the x-axis is the model computation. The y-axis is the image type accuracy. So the higher accuracy, we need more computation. So the black dot is the model designed by Google, the mobile app, where we have a large mobile app, medium and smaller image sizes. And AMC compressed model strictly dominates the model designed by human, where we can have, under the same computation, we can have error accuracy, and with the same accuracy, we can have a lower latency. So this is the latency, not the blocks. Right? So this is the human designed mobile app baseline. And this is the learning-based pruning method, which outperforms the rule-based method, human design model without optimization from AMC. So we can accelerate running deep neural nets with mobile devices. Phone. Originally, the mobile net runs about 119 milliseconds, but but we can accelerate by about 1.8 times, only about 64 milliseconds. Well, the top one accuracy is pretty much the same, only 0.1% loss of top one accuracy. Well, we can also save the memory from 20 megabytes to only about 40 megabytes. We can more aggressively improve the model to about 2x speed up. But still, it works much better than the human design model, where it's about 10 milliseconds faster, and also about 1% better top one accuracy. So we realized this goal that when we are given more customers, we can have an AI engine to do the automatic model compression rather than relying on lots of human engineers. All right, so another question came to us. So rather than compressing an existing model, right, we take ResNet, take MobileNet, and then compress it, can we design an efficient model to begin with? So conventionally, one model runs on different hardware. For example, ResNet runs on TPUs, it runs on GPUs, it runs on mobile SoCs, it runs on FPGAs. But different hardware have completely different architecture and different demand for computation. So can we design a specialized architecture, neural network architecture, given a different characteristic for hardware? For example, can we design specialized model for TPU? Can we design specialized model for GPU and mobile SoC? So our work is trying to design specialized convolutional neural nets for a target hardware. So we need algorithm hardware co-design, but the design space becomes even larger. Right? You have so many layers, you have different knobs to tune. But engineers are very expensive. You don't want to rely on human labor to do such design space exploration. Therefore, we need design automation for deep neural nets. So that's what I'm trying to describe in the next couple of minutes. I'll introduce our recent work, recently accepted by ICLR, the proxylase NAS, the direct neural architecture search on target task and target hardware. So NAS stands for neural architecture search. So we want to search automatically an efficient architecture that are both run fast and also accurate. Proxylase means we don't rely on proxy tasks, and we directly search a fast model that runs on the target hardware. But such a task is very difficult, right? To have a specialized neural net for different hardware. The most challenging part is the search is very expensive. For example, the first work from Google about neural architecture search to 48,000 GPU hours. If you have one GPU, that needs to take about 5 years on a single GPU. And such task is also memory intensive. Another work from DARTS, it will take 100 gigabytes of GPU memory if you do the search directly on ImageNet. So we want to do the model architecture search, not relying on proxy task. The first thing to solve is to save the computation so that we are able to search on large-scale ImageNet directly, and also rather than rely on small architecture space, we can directly search on large architecture space. Rather than relying on a few epochs of training, we can do the full training. So this is what we propose to learn an architecture directly on the target task to give good accuracy, and also on the target hardware to give good latency and update the learner. So we want to reduce the cost of NAS to the same level of normal training. And we also use direct feedback from the hardware into the search process. So the model is not only accurate, but also is fast. However, the challenging part is we don't have a lot of GPUs. In Google, basically ambient research institutes, there are lots of high-end GPU clusters and many engineers to search efficient neural net. Right? But in our lab, we have only 2 students working on this task. And the GPU is also limited GPU resources. So really, we are constrained by the poor equipment. But luckily, students have smart algorithms, just like here, 小米加步枪, we are given only very poor equipment, only 2 students, but we can search even better model in Google using so much, a lot of high-end GPU clusters. The reason is we have smart algorithms. So the way we achieve 小米加步枪 is by using model compression, the ideas over there, to do neural architecture search. So we apply pruning to save the binarization to save the GPU hours and the GPU memory when we are doing the architecture search. And in particular, to save the GPU hours, we prune away those redundant paths based on those architecture parameters. So we have many candidate paths when we are doing the neural architecture search. For example, one layer can be 3x3 convolution, or 5x5 convolution, or identity mapping, or pooling layer. We put all the candidates in the action into the search space. But after we search a good model, we keep only one path and prune away those redundant paths. And also we have not only those architectural parameters, not only those weight parameters, but also we have a lot of architecture parameters to control which path do we take during the architecture search. In order to save the GPU memory, we binarize the path to the path level binarization, and we save the GPU memory from O1 to O1. So we have lots of candidates, but only we allow one of them in the GPU memory. And we provide both gradient-based and RL-based methods to update the binarized parameters. Conventionally, when we are doing architecture search, the model can be accurate, but may not necessarily be fast. So we want to have the latency as a direct feedback. So we build a latency model. Given the architecture parameters, the probability you take each path, you can have expected latency by multiplying the probability of each path with the latency, which you can pre-build a lookup table. And finally, our latency model is pretty accurate. So this is the estimated latency. Given this hardware, given this model, estimate how much time does it take. And this is the real latency. It's very accurate, only 0.75 mean square error on the task. So this is meaningful when we are running deep neural nets on the mobile phone. Since the measure of the latency is has very high variance, especially due to the thermal throttling. When the phone gets hot, it will run slowly. All the research is no longer accurate. So my students joke on me saying, luckily we are in Boston, right? We can go outside, which is pretty cold, to measure the speed on the phone. But with this latency model, we don't have to do that. Just use this model to give an estimated latency. But it's still pretty close to the real latency. So this is the result we achieved first on Cypher and then ImageNet. The first group are all human-designed models. And the second group are all AI-designed models. All this work you can see actually they're from Google. And the reason is Google has a lot of computational resource, which is very good. The last one is our work. We achieved better error rate in Google, but we use only 6 times less parameters. And also on ImageNet, compared with the blue line, which is the mobile version 2, which is the current industry standard. If you have an Android phone, it's highly possible one of such models running in your phone. The x-axis is the mobile latency. The y-axis is the top line accuracy. So we are about 1.8 times faster than the current industry standard. The students recently pushed this value to 75% top line accuracy. As soon as we have this result released, Google contacted my students for asking them for internship. But I said it's probably too early. They don't want to quit their PhD and only after half a year. All right, so this is comparison table for mobile app, which are human-designed models. And the second group are all AI-designed models. And the last part are our proxyless NAS. Okay, thank you. All right, let's come back. So after seeing the models designed by AI, we can see these models previously outperformed the human designed models. Right? like 72% top-line accuracy to 74% top-line accuracy, and the latency is slightly the same. But the Google approach, they cost a lot of computation power. For example, this neural architecture search take 75,000 GPU hours, 48,000 GPU hours, so which is very difficult to achieve in a research lab in a university. So we cut the search cost by 2 orders of magnitude. We use only 200 GPU hours. We use 200 GPU hours, but we can outperform the performance from the previous work by about 1%, but also using a very similar under a very similar latency. And the rule of thumb is here we are hardware aware, and also we don't rely on proxy task. We have full flexibility to search to search across the whole action space, and we don't need to repeat the building block, which people has used for many years since VGGNet. VGGNet we are repeating many building blocks. MobileNet we are repeating building blocks. Now we don't need to repeat the building blocks. So not only Proxy is not working on mobile phone, but also it works on GPUs. We use the same code. Remember, we can specialize the neural net architecture for different hardware architecture. So we can have 1% better accuracy, but also we are 20% better, shorter latency than those previous work. So NVIDIA is very interested in this one. So we also proved that the latency is actually specialized model works best when you are searching your model for your target hardware. For example, the GPU model works best for GPU, but not the best for CPUs. So the diagonal entries has the lowest latency, which further motivates the need, the demand for specialized neural net architecture for different hardware. So this is a demo for the search history for different epochs, for the mobile phone, for the CPU, and for the GPU. We can see the GPU aggressively used 7x7 layers, which is in red. The yellow one is 5x5 convolution, and the blue one is 3x3 convolution. The GPU model has shallower models, but wider models because it has more parallelism. The CPU model doesn't use any 7x7 layer, and also it's deeper. And we can see during the pooling layer, it becomes wider because it loops to prevent losing information, which means the AI agent actually learned something when it designing neural nets in the final epoch, after dynamically growing the model and shrink the model, finally stabilized at the final architecture. So this is the final architecture. We can see for mobile phone, for GPU, CPU, and mobile phone, the optimal architecture is actually quite different. So many people contact us, try to use this model. So we open source the Proxys NAS model on GitHub. We provided both the CPU model, GPU model, and the mobile model. You can actually use these 2 lines of code to deploy it. And recently, as requested by Google, the TensorFlow team, we also open source the TensorFlow version. So both PyTorch version and TensorFlow version are available. So feel free to use. If you have any questions, feel free to contact me. All right, so how in talking about neural architecture search and also model pruning, can we automate the design of quantization, right? Especially recently, lots of hardware begins to support multi-precision. For example, in the Apple release of the A12 engine, there's a small note that it has multi-precision support. And also for NVIDIA GPU, it supports various different precisions like FP32, FP16, int8, int4, and most recently int1. Which raises a question for different layers. How many number of bits do we need for the weight? And how many number of bits do we need for activations? This is a pretty big design space. Say we have 8 choices for the weight, 1 to 8, 8 choices for the activation. That is 64 choices for each layer. And if you have n layers, That's 64 to the n number of choices, which is pretty huge. So we want to automate the design by, again, using a reinforcement learning agent to decide the best quantization policy. And we want to take the hardware feedback into the design. When we have inserted a hardware accelerator to direct the feedback for the latency, the number of cycles, and also the energy it takes to run this compressed model. So we evaluated not only for one architecture, but also for both the edge accelerator and the cloud accelerator, two different architectures. One is BISMO, one is Fusion. So our multi-precision support outperformed the human rule-based optimization method. By using the same latency, we can have a higher accuracy and smaller model size. So this is the process of the accuracy guaranteed exploration, where the agent first learns to increase the accuracy, in phase 1. And in phase 2, after a small exploration, we realize we can reduce the latency without hurting the accuracy. So we're reducing the latency and reducing the energy. And finally, after another trial, it sees if we increase the latency and energy, it doesn't help with the energy. So finally, it's stabilized. Right? So what does the agent learn? This is for all the layers for MobileNet version 2. We can see it is very regular. We have up, down, down, up, down, down. So for depth-wise convolution, it gets allocated with more number of bits. And for the point-wise convolution, it is fewer number of bits. This is because the point-wise convolution has more parameters. So if you give fewer number of bits, you will have a better compression ratio. And you see also the last layer, the agent learned to allocate less number of bits for the last layer, because the last layer has a lot of parameters. So if you have fewer bits per layer, it will save you more parameters. So the previous slide shows the result for compression, but for improving the latency, for acceleration, the compression policy is actually the reverse. It's quite different. So for MobileNet version 1, we find for acceleration, the depth-wise convolution gets allocated with fewer number of bits. The point-wise convolution gets allocated with more bits. And why is that? So we analyzed the computation ops per byte, the computation over memory, the computation intensity. We find they align pretty well. So for the steps-wise convolution, they have a pretty low computation to memory ops per byte, which means it's memory bounded. And for mobile devices, edge devices, it's memory constrained. Therefore, those layers get allocated with fewer bits because they are memory bounded. However, on the cloud, the policy is exactly different. Since on the cloud, we allocate more memory bandwidth, so it's computation bounded. Therefore, point-wise layers are computation bounded. Therefore, the agent decides to allocate fewer bits for those point-wise layers. So the take-home from hardware-aware quantization is we want to have a quantization policy hardware-aware. Different hardware, we may have completely different quantization policy. And also, we need to automate the process, since this is very labor-intensive if you do it by human. Finally, we want to have a specialized design, right? For different tasks, for different hardware, we want to have a fully specialized way of doing that. Previously, in the hardware community, we want to have a specialized silicon for algorithm. Now, it seems quite important to have a specialized algorithm for different hardware. All right. So far, we talked about 2D images mostly. So now let's switch gear from 2D world to the 3D world. From 2D convolution to 3D convolution, which is more computation intensive, but also more interesting and challenging. Especially in videos and 3D shapes. 3D convolution is widely used. And I will show our recent work on TSM, the temporal shift module for efficient video understanding. So video standard is getting quite popular in recent years as advertisement and also the short video like TikTok is getting quite popular. And you need to analyze the video to understand what is the action in order to either insert the advertisement or do censorship. So an important goal of our work is to do efficient spatial and temporal modeling. We want to not only extract the features from the spatial, but also extract those temporal features, which is quite important. Say, if you're moving a tape from left to right, if you just see a single image, you cannot tell whether you are moving from left to right or you are moving from right to left. So you need to look at the whole stream of multiple frames per second. A conventional way is to use 3D convolutions, right? That can converge to do joint spatial and temporal feature learning. But the drawback is 3D convolution is very computation intensive. But 2D seeing is computation efficient, but it cannot handle those temporal models. Therefore, our goal is to achieve 3D seeing's performance and 2D complexity. And how do we do that? So after we sample several frames from a video stream, for example, here we have four frames, T0, T1, T2, T3, and T4, corresponding to those yellow, blue, green, and red frames. This direction is the channel direction. This is the X and Y feature map. So conventionally, 2D convolution, we want to do them individually, but that cannot model the temporal information. So for 3D convolution on the temporal domain, convolution has two parts, right? Move or shift, followed by multiplication and add. So we explicitly do the shift in the channel direction, where we shift 1/4 of the channels to the bottom, 1/4 to the up, and keep half of them unshifted in the temporal domain. So for example, in T2, now we have the channels from T1, from T3, and also T2. So one channel, actually, you see 3 different timestamps. So if you cascade multiple such modules, you can see the entire video. So we examined the performance on two categories of tasks. The first one includes use of HMDB and also kinetics, where you can tell what is it doing just by a single image and typing and playing hula hoop and other activities. The other part is temporal related, like swiping from left to right, thumb up, or other activities. So we expect to have a better performance on these more temporal related tasks. And the performance exactly matches the observation. So on those less temporal related tasks, the improvement is decent, but not too much. But 3%, 4% improvement of accuracy. But compared with the 2D methods, on those more temporal related tasks, we improved the accuracy by 20%, 13%. It's quite impressive, because these tasks, like gesture recognition, heavily relies on temporal modeling. So this is a big chart on something data set. If you want to see one number, you want to see this number, where we are ranking top first in the scoreboard on both something V1 data set and V2 data set. And we also saved the computation. This is probably a better summary than the Excel. So given fewer floats, we can achieve better accuracy than those I3D-based methods and also ECO family. So here is a demo about the speed up. We measured the TSM on the P100 GPU, and the conventional I3D method, the latency is roughly 164 milliseconds per video. The accuracy is 41.6%. And we can speed up the latency by 8 times without changing the task accuracy. Actually, we improved the accuracy from 41.6% to 43%. Now you can run each video at only 20 milliseconds per video. So not only accuracy, latency, but also the throughput got hugely improved. So this is again measured on Tesla P100 GPU. So on the left-hand side is the I3D method, previous widely cited paper. It runs 6 videos per second. But after our TSM acceleration, we can run 7 videos per second. This is quite significant because the throughput determines the price, the cost of your service. Previously, let's say you can serve one customer with a GPU. Now you can serve 12 customers. So the cost becomes much lower and you have more margin of profit. This is another demo showing the effectiveness of TSM doing temporal modeling in a something data set. So this data set is saying heating something with something, moving something away from something, trying to tell the relationship what you are doing. Turning something with something. It doesn't tell the exact object because it focuses on the temporal model, building something with something. And we can see TSM is quite good at modeling this temporal information. We have another demo for gesture recognition, doing gesture recognition on an embedded platform. So we have one camera view and a screen view. So we are using TX2, NVIDIA Jetson TX2. As the mobile GPU, you see the fan is not working, it's taking only 5 to 7 watts. It's running about 15 frames per second. This is the prediction of the gesture, moving left and right. Moving on 2 fingers. This can be quite helpful in autonomous driving where drivers can control the map, control the car inside when you are driving without touching the screen, and zooming in the map, zoom out the map, and just using your gestures for controlling the robots. All right, so far we talk about various different automating methods, try to make AI run much faster and more efficient, given a better chip or given a better system. Now we want to see the other direction, where can we use AI to design IC, or at least assist us to design IC? AI is a good cat tool. So rather than relying purely on human engineers, can we use AI to help with the design process? So the goal, similar to other design automation, we want to save the labor of circuit design or IC design to have more AI to help generalize human experience into the chip design. So we started with analog IC design because analog IC are like digital, where design house can have a very automated tool to do that. So analog design previously relied on human experts and rely a lot on engineer experience and intuitions. There are very few rules to follow. It is time consuming and maybe suboptimal. So the goal, we started by search the analog circuit parameters. It shares a lot of common features with deep neural nets, where neural network it is a graph, it's a directed graph. Circuit is an undirected graph, but both of them can be represented as graphs. We want to let's rely on human labor and speed up the design and get better performance. So this is our initial trial of optimizing circuit parameters using a sequence-to-sequence model. So sequence-to-sequence model previously is widely used in machine translation. Say in Chinese, we translate to English. But we find circuit can be modeled as a sequence, right? You have, say, 3 stages of an amplifier has 3 stages. Then from stage 1, stage 2 to stage 3, that is a sequence. And then we can, in the output sequence, we can give the transistors according to the stages, the W and L, and the resistance, the capacitance for each device. So in the observations, we feed the DC operating point and also the amplitude and phase response of the previous setup to the circuit. And also we put the transistor observations at BTHG and BTSat. Those parameters feed into the deep neural net. So we tested a circuit. Previously, this is a design at Stanford EE214B class, the advanced analog IC design. And the baseline, the human expert is one of my friends. He received the most innovative design award in Professor Boris Merman's advanced IC analog IC design course. So compared with human design, where the score is normalized at 0, the AI design optimized parameters get very close to the human design. Right? We haven't surpassed human design yet, but it's getting pretty close. I need to mention that human design took about 1.2 million simulations, very exhaustive search. But the AI agent took only 50,000 simulations, 25 times less simulations, more sample efficient. You see, this is the spec. And the AI design model meets all the specs. And noise may be a little worse than the human design models, but like the power is much lower. So compared with human design models, the Bayesian optimization given under the same search cost, some of the design specs didn't get violated, so it's not quite effective as the learning-based method. This is another project, Centric EE214A class designing this amplifier. And reinforcement learning-based method even surpassed the human design, and also with 250 less number of simulations. And better meet all the specs for bandwidth, gain power, gain area, etc. All right, so to sum up, today we talk about the big picture of design automation for neural networks, right? Especially for hardware and algorithm co-design, the design space is very large. Human experts is very difficult to take advantage to aggressively search the design space. So we want to have automated tool chain to use AI to do the design space exploration. So previously we have lots of data, lots of computation, and many engineers. Now we want to have machine intelligence to help with the engineering experience so that we have less reliance on human engineers. Just given a lot of data, given a lot of computation, we can automatically find a solution. Such design automation will be very helpful for reducing the cost to save human labor. Everyone can move up the ladder and do something more meaningful. So in summary, we first talk about previous work on model compression, DeFi's Deep Neural Network Development Kit, DNDK, and also the efficient inference engine that directly accelerates the sparse and compressed model. And later we motivated several works on the design automation for efficient neural nets, like using AMC to automatically do model compression, using Proxys NAS to automatically using AI to design deep neural nets for target tasks and target hardware, and using hardware-aware quantization to automatically do quantization for different layers given the hardware constraints, and also using TSM, a temporal shift module, to effectively do video understanding and improve the latency and throughput. And finally, learning to design circuits. Can we use AI to assist with analog circuit design? So for more information, you can reference my website for the details for all the projects. So finally, this is a picture of my lab recently renovated at MIT. This is the new meeting room. This is the office together with some lab space. It's getting quite beautiful in the summer. You're going to visit the Charles River, and the sailing is getting quite exciting. So we have some accommodates visiting students. So if you want to do something together, you can contact me, and hopefully we can have more interaction in the future. All right, thank you. So very appreciative. Thank you.